Okay, so let's see if we can follow this discussion on limits. Now I'm going to be a little bit more careful in going over this section because it's important to develop an intuition about limits as well as to understand the rigorous definition. All right? So he says the goal is to achieve rigor without rigor mortis. So you want to mix your rigor with your intuition. We've been talking about limits of delta y over delta x, where both delta y goes to 0 and delta x goes to 0. But now let's talk about some other limits, more general context. All right, and I hope you can see how these things work. Here I have a sequence an, right, where n is 1, 2, 3, dot, 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 and an is n minus 3 over n plus 3. Now what happens when n gets bigger and bigger? Now you can see n starts out when n equals 1, I get minus 2 over 4, so that's minus a half. When n equals 2, I get minus 1 over 5, so that's negative. When n equals 3, I get 0. When n equals 4, I get 1 over, let's see, what was I saying? When n equals 4, I get 1 over 7, which is small. All right, so this kind of, so if you plotted these numbers, you would see that they're actually increasing. You can do that as an exercise and plot these numbers. But what you want to think of here is what happens when n gets very, very, very big. All right, so for instance, suppose n is 1,000,000. Then this number on the top is 1,000,000, 1,000,000 minus 3, which is 99997, and this is 1,000,000 plus 3. Now, if you divide those two numbers, you can try that. You'll see that that number is very close to 1. Why? Because the 3 is much, much smaller than the 1,000,000. And the 1,000,000 is dominating the numerator and the denominator. Another way to see this would be divide the top and the bottom by n. If I divide the top by n, I get 1 minus 3 over n. And when n is big, 3 over n is very small. Then on the bottom, I would have 1 plus 3 over n. Same deal, 1 plus a very small number. So as n gets bigger and bigger, this is getting closer and closer to 1. All right, and in fact, the limit of an as n goes to infinity is equal to 1. All right, let's look at this one here. All right, so suppose we take an and take 1/2 of an minus 1 plus 4. All right, now you can try this. You can start with any number and see what happens. For instance, if I start with 0, then that would be a1. Then I get a2 by taking half of 0 plus 4. Now that's 4. Then if I get the next one, I take half of 4 plus 4, which is 6. If I take half of 6 plus 4, that gives me 7. If I take half of 7 plus 4, it gives me, well, that's 7/4 plus 4. I think that actually turns out to be 7 1/4, something like that. And if you keep on trying that, you will find out that you always get a number close to 8. It turns out if you choose a starting number which is bigger than 8, it still goes to 8, which is kind of an interesting thing. You can prove this rigorously. One thing to notice is that if I put 8 in here for an minus 1, I get 8 back again. So 8 is kind of a stable point or fixed point and doesn't change. But it turns out no matter where I start, I'm always going to get closer and closer to 8. So the limit of an is 8 as n goes to infinity. Okay. All right, so an is the probability of living to year n. Okay, so if in this current existence, we don't have anybody living an infinite life, but you do get people living longer and longer. So eventually, if n is bigger than 200 or so, you're already going to have a probability of 0 of living to 200. So this number, an, is getting smaller and smaller. Certainly a1000 is 0, a1001 is 0, and so on. So this number actually reaches 0 and stays 0 after it reaches 0. Okay. Then here it says the fraction of zeros among the first n digits of pi. Now, you know that the digits of pi are random, so there should be lots of zeros. And no matter how far out you go, you're going to find zeros. This one's a little hard to analyze. Let me skip this one. Okay. So let's see. So here you have several decimal numbers, and what he's saying is that you can add another decimal digit, and no matter what you add a number, you're going to get some number that converges to a limit, that converges to a real number. Now, this is actually quite a profound fact, that you can create all real numbers as decimals. And that's what he's talking about. And if you chose random digits here, you wouldn't be able to express this as a fraction. You wouldn't have any way of expressing this number except by an infinite decimal sequence. But we can still call that a real number, and it's a definite real number. Okay? So in all these cases, we're talking about limits, something becoming closer and closer to something, and having a sequence, a limit of a sequence. All right, now here's, I like the way he does this. He says these things are not what it means to approach a limit. So he asked this question, what does it mean for a sequence of positive numbers to approach 0? All right. Now we can have limits approach other things like 1 or 10 or anything else. But let's start with a simple case. What does it mean for a sequence of positive numbers to approach 0? Okay. Now the idea is that the numbers get closer and closer to 0. All right. So in other words, the numbers are getting small. But that's kind of vague. So let's think about 4 different definitions, which will be the right one. One definition he doesn't have is that saying that each number is smaller than the previous. Now, it turns out that that's too strong a condition. You can have numbers that don't get smaller and smaller successively, but still converge to 0. So that's not good enough. You can have so if you say the numbers get smaller and smaller and eventually reach 0, that's a little bit too strong. All right, here he gives some other examples of definitions that don't work. If you say all the numbers an are below 10 to the minus 10. Now, unfortunately, that doesn't work because I could choose all the numbers a to be 10 to the minus 11. You're never going to reach 0. You're just stuck at 10 to the minus 11. Okay? So that satisfies this condition, but that doesn't give me a sequence that converges to 0. Okay? Here it says the sequence is getting closer to 0. Now, if you don't say that they actually get arbitrarily close to 0, you could do something like this, 1.1, 1.01, 1.001. These numbers are getting smaller and smaller, but they don't converge to 0. Okay. In fact, if you do something like this, you will converge to something, but it may not necessarily converge to 0. Okay. All right, it says, for any smaller number you think of, at least one of the ands is smaller. Okay. All right, so here's an example where that doesn't work. He takes 1, 1/2, 1, 1/3, 1, 1/4, 1, 1/5, etc. Now, no matter how small a number you think of, you can always find a number that's smaller than that. So, for instance, if I take 1 over a million, well, 1 over a million is in this sequence. 1 over a million and 1 is in this sequence. I could take 1 over a trillion. Still, 1 over a trillion plus 1 is in this sequence. So I can always find a number that's small as I like. But it keeps jumping up back to 1, so the limit is not 0. You need, in some sense, all the numbers to get 0, but get close to 0, but only if you get out far enough. So this is the correct definition. So let's take a little time on this. For any small number you think of, the ands eventually go below that number and stay below. Okay. So there's some key aspects of this definition. For any small number, typically you use the number epsilon. Okay, so the symbol epsilon rather. Epsilon means a small number. Now epsilon can be anything. I can choose epsilon. And here it says the sequence of ands eventually go below. All right, so for instance, you can if you draw this picture here. Here's my epsilon, right? And here I have a sequence of numbers. A1, A2, A3, A4, A5. All right, so we can see some of these numbers go below. All right, but here it says eventually goes below and stays below. All right, so here it went below, but it didn't stay below. Here it went back up again. But after some point, if it stays below, then it meets the criterion. Now, what we see here is not enough to show that the limit is 0. But this would have to work for any epsilon. So for instance, if I chose my epsilon down here, there should be some larger number out here, like A20 or A21 or something like that, where all the succeeding numbers are below that level. So it kind of reminds me of the game of the limbo, where you have a stick and you have to go under the, you have to make sure you go under the stick. Now what this is saying is that eventually you will always, no matter how low the limbo line is, eventually you can learn how to go below the limbo stick. Right. So if you want a picture of limbo, I'll show you. Okay, here's the game here. So so limbo, I don't know if lim has anything to do with limit, but this is how you play the game. You have set a bar and you have to go below, and you set the bar lower and lower until the person who gets under the lowest bar wins. Now, what the limit means is that no matter how low you set the bar, the numbers can always go below, and after some point, they will always succeed in going below. Now, they might miss a few at the beginning, but eventually they can always go below. All right, so that's the definition of limit. So you can think limit and limbo. Okay, all right. So here, so let's look at a example here. It says the ends must go below any number, so that they eventually must drop. All right, let's look at the sequence: 10 to the minus 3, 10 to the minus 2, 10 to the minus 6, 10 to the minus 5, 10 to the minus 9, 10 to the minus 8. So what is the way this is going here? You have to see how this is working here. It's not really very systematic. It looks like you take 10 to the minus 3, and then you multiply that by 10. Okay, and then looks like you take, let's see, what do you do next? Then here then you subtract 4. Then you divide by 10,000. So here I multiplied by 10, then divided by 10,000. And then multiply by 10, then I divide by 10,000. I multiply by 10, divide by 10,000. Now, they're not going down monotonically. They're kind of going down, down, and then up a little, down, and then up a little, down, and then up a little bit. Eventually, these numbers will get as small as you want. Okay, even though they don't go steadily down. All right. All right, let's look at this one here. Here I have 10 to the minus 4, 10 to the minus 6, 10 to the minus 4, 10 to the minus 8, 10 to the minus 4, 10 to the minus 10. Okay, this does not stay below 10 to the minus 4. This is the same thing as this one up here. You've just made the bar a little bit smaller. But you still cannot arbitrarily decrease the bar down and down. It's always going to miss if the bar is below 10 to the minus 4. Okay. All right, so convergence to 0 means the sequence eventually goes below epsilon and stays there. Okay, the smaller the epsilon, the tougher the test, the longer we wait. So it's like the limbo game. You set the level lower. It may take longer to learn to get under it, but eventually you can learn to get under it every time. Now, so far we've been talking about limits of positive sequences. But you can also have numbers that are positive or negative. Well, what you do is, if you have a sequence of positive and negative numbers, you turn it into a sequence of positive numbers by taking the absolute value. All right. So if you have a sequence of positive and negative numbers, the limit of that sequence is 0 if and only if the limit of the absolute value of those numbers is 0. Right? So an goes to 0 means the absolute value of an goes to 0, and vice versa. If absolute value of an goes to 0, then an also goes to 0. And what that means is that basically, instead of having a stick like this that you go below, you actually have a strip that you go inside. Eventually, the sequence gets inside the strip, and you can choose smaller and smaller strips. All right, so that's what limit means. Okay, so you have that intuition, and then here's the formal definition. For any epsilon greater than 0, should be epsilon greater than 0, there is n such that an minus L is less than E if n is less than n. Okay, I forgot to mention something here. He's talking about limits other than 0. If an goes to L, that's the same thing as n minus L goes to 0. Okay, so that's why just convergence to 0 gives us all limits, because we can transform a limit statement about going to L to a statement about going to 0. Right? And you can see the picture here also. This is a limit statement about going to 0. Here you have the strip. You have a small strip here, and the strip can be made smaller and smaller. Now, if I want to find the limit is L, I just move the strip so it's around L. All right, so that's kind of the intuition there. Now here's an interesting case of a sequence. 1, 1 plus 1/2, 1 plus 1/2 plus 1/3, 1 plus 1/2 plus 1/3 plus 1/4. Next one is going to add another 1/5, add another 1/6, add another 1/7, and so on. Now it looks like this sequence is converging because you're always adding one fraction, and the fraction you're adding is getting smaller and smaller. But it turns out the sequence does not converge. Why is that? Even though the numbers that you're getting are smaller and smaller, you still get a divergent sum. You may know the harmonic series. That 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. This does not converge. This increases indefinitely. All right. And here he has a little proof of this. So anyway, the upshot here is that if you're adding smaller and smaller terms, that's not sufficient to guarantee that the sequence has a limit. Okay, so in other words, if I take the difference between two terms, and that difference is getting smaller and smaller, it's still not true that an has to converges. And here's an example, right? Because the difference between an and an minus 1 is just 1 over n, which certainly goes to 0, but this sequence does not converge. On the other hand, if you do have a convergent sequence, then the difference between successive terms must converge to 0. Okay, so this is a case of where if is true, but the only if is not true. Okay, so if an converges to L, then the difference between successive terms converges to 0. But it's not true that if the difference between successive terms converges to 0, then an converges to L. Okay, so he's going to talk a little bit about logic below. Okay. All right. Now, I think you should have seen this in discrete mathematics, but it's probably good to go over this again. So here it says A implies B is the same as if A then B, which is the same thing as that A is sufficient condition for B. Means A is true, that implies that B is true. So this is B is true if A is true. This seems a little confusing. Here you have the if A then B. Here you have B is true if A is true. But the if goes on the A. A is the condition. If the condition works, then the result works. A is the condition, B is the result. So that's how if then works. Okay. Now you can also run this backwards. A is implied by B. And if B, then A. A is necessary for B. In other words, if A is not true, then B cannot be true. B is true only if A is true. All right. So that means, one way you can do this is take the example of Colleen and Texas. If I'm in Texas, let's see, I can't conclude that I'm in Colleen. But if I'm in Colleen, then I'm certainly in Texas. So if I'm in Colleen, then I'm in Texas. On the other hand, I could say, if I'm in, I can only be in Colleen if I'm in Texas. So B is in Colleen. Being in Colleen is true only if A is true, A is being in Texas. All right. Now here you have if and only if, which means both ways are true. It means they mean the same thing. And this is what I was saying above, that the sequence an converges to 0 if and only if the sequence absolute value of an converges to 0. Okay, we do have some rules for limits. If I have two sequences, I take their sum. Then the sum of the sequences converges to the sum of the limits. Okay. Same with subtraction. Two sequences, I take their difference. The difference of the sequences converges to the difference of the limits. Same thing with multiplication. Same thing with division, unless the limit of bn is 0. Okay. All right. All right. So here it does a proof here of the multiplication rule. I think I'm going to stop here. I think I'm going to have to break this video up. I don't want to make it too long. So we'll stop there, because here he's talking now about limits of functions instead of limits of sequences. It's a little bit different. All right, so hopefully that helps some.